Morning, everyone. So yesterday we had a look mainly at the physical characteristics. We started looking at matter. It comes in many shapes and sizes, but all matter should have mass and volume. We know matter comes to us in three common states of matter: solid, liquid, and gas. Primarily when I convert them, either adding heat or taking away heat. It's not called a chemical change because nothing new is produced. None of the bonds break or form. The chemical is exactly the same before and after. We also, towards the end, we looked at a few physical ways of actually separating different mixtures. So whenever chemicals are all blended up together, it's a little bit hard to isolate and analyze. So first thing that we want to do is we want to, depending on what the mixture actually is, if it's undissolved solids, if it's things that have different boiling point, things that have different solubilities, we can use one of those techniques that we talked about in yesterday's lesson to break them apart. From here on out, we're going to focus more so into the chemistry. Chemistry you learned yesterday was a study of basically understanding the composition of matter, how things are bonded together at that microscopic level, and somehow giving it all the macroscopic appearances and behaviors that we see along with the reactivities. So today we're going to start into what's called their nomenclature section. Nomenclature is just a fancy way of saying naming. Now when we do naming here, sometimes they call this guy here IUPAC naming. I just want to introduce this acronym to you here. That word IUPAC here actually stands for the International Union of Pure and Applied Chemists. So basically this is a global group basically made out of chemicals from around the world, and they basically set all the rules for chemistry. All the naming you've done up to this point, talking about ionic compounds and covalent compounds, the next two lessons or so, all of them are set by rules from IUPAC. So pretty much whenever we do nomenclature, whenever we do naming, it's always using this IUPAC system. All the exceptions and all the little rules, oh, here's where you need the prefix, here's where you can drop the prefix, all of them were set by IUPAC. So anytime they say write the IUPAC name, it's pretty much the naming that we are used to. So let's just start off here. Some of this will definitely be reviewed from earlier science classes, but again, I just want to make sure we're all on the same page as we continue forward. So based on the way IUPAC set this up here, we can set up a quick table here. We can identify for us here every element, every different type of material. That's called the element. Yesterday we had said element was down the strand of this is a pure substance. Elements are just sort of one type of material. In fact, with the periodic table, if it is the periodic table elements, pretty much if you can find a square on it on the periodic table, you know it is an element. Let's set up a table here with element as one of the headings. The other heading here, I'm going to call it here chemical formula. Now, usually in math class, when you think formula, you think equation, you think Pythagoras, something like that. In this case here, the word formula just indicates, because sometimes the name of the element here is fairly long, I don't want to keep repeating it over and over again. The chemical formula just represents the symbol. So just a shorthand way, we see that when we actually do the symbols here, it actually gives us extra information. It gives us sort of what ratio between the different elements here, somewhat more information than just the word name by itself gives you. For these chemical formulas here, we're going to see that they're either one or two letters. The first letter is always capital. Let's start off here. Our whole periodic table is based off of carbon, so it's a very important element here. So carbon starts with C. The chemical formula here is just capital C. Sometimes it is two letters, so let's look at the element, let's say neon. I could have picked any one of these here. For neon, if you look at your periodic table, it is two letters. The first letter has to be capital. Make sure the second letter is lowercase. It's incorrect if you actually say neon like this. Okay, so first letter is always capital. If you have one letter, definitely it's capital there. Sometimes it's first letter and then one later letter coming up. So let's do the element here, manganese. Okay, careful, manganese is a different element from magnesium. Manganese is actually using the M from the beginning and the N from later on. And this one here is capital M, lowercase n. Magnesium would have otherwise been Mg. Some of them I just really don't understand here. If I take a look at, let's say, gold, I would expect, well, it's G or GO or GD or something like that. In this case here, if you look at your periodic table, it's actually AU. This is because, again, this IUPAC group here is a global group here. A lot of this science here, as it was developing, a lot of it actually didn't originate in English. In this case here, some of the elements actually have Latin roots. I'm not going to be asking you for these Latin roots here, but if I told you the Latin root, for example, for gold is actually aurum, we can sort of get an understanding here. Well, it may be just that AU that they're representing the symbol with. Even in our IB data booklets here, there is a section that gives you, here's the word name of the element, here's the atomic number. What we're going to see is the proton number actually makes the different elements, and along with the symbols. On their periodic table itself, they actually just have the symbol. So the goal here is hopefully you'll be more comfortable using some of the more regular elements, and once you have those elements there, you can be pretty easy naming the compound. If I give you the word name, you can write the symbol. I've just copied a picture of the periodic table that I'm going to be giving you here. This table was borrowed out of the regular grade 11, grade 12 textbook here. Your IB data booklet will have a very similar table, albeit the font is a little bit smaller. As you look at that periodic table just as a whole, what are some things you notice are different than the ones that you see from your grade 10 tables? So your grade 10 tables here, if you just compare it, if you still have it maybe, or just Google it here, you're going to find your grade 10 tables here. They gave you a lot of extra information. First thing is they give you a nice stair-step division here. The stair-step here divides us between what are called metals and non-metals. You do want to keep in mind that we have metals on the left-hand side. I think on the grade 10 table they actually label that for you. Not too hard to memorize that. So metals and non-metals. We'll come back and we'll take a look at some of their common properties in a second here. So metals as well as non-metals here. We talked about rows on the periodic table. We're going to do a whole chapter on naming these ones here. The rows are called periods. We start from period, so rows are horizontal. We start from period number 1, period number 2. We're going to get to this in a later chapter. The period number actually identifies for me how many shells the element has. We're going to talk about the group number. Groups in the past used to be called families, because chemicals that were put sort of up and down from each other here, these chemicals here happen to behave the same. So pretty much all of group 1, with the exception of hydrogen here, all these guys behave the same. Group 2 all behave the same. They were look-alike, so they were pretty much identical. IB does prefer this sort of counting as well. Groups 1 all the way through 18. 18 would be our noble gases. We're going to see in chapter 2 that these inner rows here, these row 3 to row 12, those what would otherwise been called transition metals, these ones here, the electrons that actually get added are actually added to inner orbitals. So if I can ignore those 10 electrons that are added between group 3 and group 12, I could sometimes call group 13, I can refer to that as group 3, group 14 as group 4, all the way to group 18, which is group 8. And in that case there, that actually identifies for us the number of valence electrons. Again, we'll get into this. Today we're mainly looking at just introducing some basic trends and also just introducing us to the periodic table. The one big thing you should notice here, before we look at a few more things here, you should notice that the grade 10 table was really nice to you, that for every single element on the periodic table, they gave you the charge. For this, so they said, lithium, oh, when it forms charges, it's +1. Sodium, +1. Potassium, +1. Maybe iron, +2, +3. Maybe zinc, +2. You'll notice for every individual element itself, it gave you the charge. Starting from grade 11 and onwards, along with our IB table here, we're not given those charges. Now don't worry. Yes, there will be some things that we do need to memorize. There will be a handful of elements here. These transition metals here, which happen to have many, many charges. Some of them are actually listed already in the data booklet, so you don't need to memorize those. But definitely for some of the more common trends here, chemists are super lazy. If they can get away with giving you less information, they would. So in this case here, for example, I'm noticing, hey, these ones here, what we call alkali metals, are all +1. As long as I memorize alkali metals, when they bond, they typically want a +1 charge. I don't necessarily need to have all these +1s in the row here. So that's one thing you're going to notice here. We don't actually have those charges or those oxidation states because some of them just follow the pattern. So what I'm going to do with you here is I'm going to sketch out a periodic table like this. We'll talk about some of these common properties, and then we'll see some of these common names that I do want to know. On the back of this table here, there's actually some common charges. So I mentioned transition metals here. For example, iron can be multiple charges. Instead of actually giving you the charges directly there, they actually give you, oh, iron can be in the 2 form or the 3 form when bonding. Some of them can actually be found on the table. You're going to notice here they separated, these are cations. Cations, we said yesterday, cats are positive creatures, so those are positive ions. Those ones that had lost electrons. Metals tend to form those, and they're going to eventually have the anions down here. Anions, it's like eating an onion, so very, very negative. Okay, so those ones that are negative. We are going to introduce to you polyatomic groups later on this lesson. Polyatomic groups are like molecules. They're groupings of many atoms that are attached together, and yet because they are a polyatomic ion, as grouped together, they still have a charge. We're going to find that the majority of the polyatomic groups here, so let's say CO3 minus 2 here, that's given a common name carbonate. Most of our polyatomics are actually anions. Most of them are actually negative. So we'll come back to this as we take a look at the naming some more. I'm just going to take a quick sketch of this periodic table. I'll leave a periodic table on the side in the reference column so you can just download it for yourself here. But for today, let's just look at some general trends. So we talked about here dividing metals and nonmetals. So let's just talk about some general properties here. Metals typically are on the left-hand side. We get more metallic. In fact, the farther away we get from the stair-step line here. What are some common properties you can tell me about metals? You can talk about the state of matter. So metals generally are going to be solids at, I'm going to say RTP, which is room temperature pressure. In our regular exposure to them, these ones here are typically solid. The bonds that are holding the atoms together, even at room temperature, there's only enough energy to be vibrating in place. It's not enough to melt. It's not enough to boil yet. Of course, if you then heat up the metal, you can liquefy the metal. You can even get a gas of a metal if you're at weird temperature, weird pressures. But at least for our everyday exposure, solids. Some other properties here for metals, they typically, from yesterday, we talked about two intensive properties. Metals tend to be both malleable as well as ductile. Malleable here refers to it being able to be flattened out into a nice sheet, whereas ductile, if you just stretch it out, pull it out from both ends here, you're going to end up stretching it into a nice wiring. That's why we use copper as our metals. We can stretch it out really nice and it doesn't crack or fracture on you. The other property why we use our wiring on a metal is because metals happen to be good conductors. When we use the terminology conductor, we actually refer to two types of conduction. First, we refer to electrical conduction. So like a copper wiring can carry charges, can carry current. So that's a good conductor. It could also be thermal conduction. Fortunately for us, metals are good at both. We make our frying pans out of metal because you stick your pan on the stove, it doesn't take forever to fry your eggs. So those are good conductors here. We'll do one more one. They do typically have a very shiny luster. Luster is the fancy word for sort of being really reflective. So those are metals. Let's contrast them with nonmetals. So first thing, we don't have as many nonmetals. They're the ones on the right-hand side here. Pretty much they have the opposite trends of what I just wrote here for metals. So in our everyday exposure to them, at room temperature pressure, these are typically going to be gases or liquids. Again, this is a broad stroke here. There is some chemicals, for example, iodine down here. Iodine is actually a solid, so be it, that's fine. But just in general, nonmetals typically are gases and liquids. Instead of being malleable and ductile, we refer to them as very fragile. The wording we use is they're very brittle. Now, the reason we don't have a very intuitive feel of that is because nonmetals are already gas. I'm not expecting you're waving your mallet around the air, trying to beat the air molecules around. What you would have to do is take something in the air, let's say nitrogen. You need to cool it down to some negative 150, negative 200 or so before it liquefies. That's where we get liquid nitrogen. You keep cooling it down here, keep stealing away the kinetic energy, and we end up getting solid nitrogen. If I take a solid nitrogen block in front of you, you take a hammer to that one definitely cracks on you. It does not flatten into a nice foil. It doesn't stretch into nice wires. Instead of being a good conductor, usually we just say poor conductor. Sometimes you can throw in the term it's an insulator, so it doesn't really carry charges very well or heat very well. And in terms of not being shiny or reflective, this one here typically is referred to as very dull. So it doesn't sort of reflect light very well. There is a little bit of disagreement with where the stair step should actually be, but you would imagine here if the stair step divides metals and nonmetals, we have some grouping here which should have properties of both. IUPAC here had named these guys here. These ones here are called metalloids. In the olden days, we also called them semi-metals. They had sort of some properties of metals, some properties of nonmetals. Maybe they were malleable and ductile, but maybe they were dull. Maybe they were good conductors, but maybe they were brittle. So they actually have some combination of properties. As we study this some more in Chapter 3, we're going to see they actually have the best of both worlds. They have the strength of a covalent bond, like nonmetals do, and they have the lattice that ionic bonds do, and that's why they're so incredibly hard to melt. So more on that in the later lesson. As I mentioned here, the first big surprise is in these periodic tables, we're not given those charges. So of the ones that we have to memorize, I'm just going to set up a chart for you. We're going to number our groups. Remember, our groups are vertical columns. They give us the number of valence electrons. We're going to start from group number 1. Although hydrogen is also in this group here, I'm going to actually start my group here starting from lithium and work my way all the way down to francium. I'm going to give you, so that's called group number 1. Let's set up another table here. The number of the group. We're going to qualify the common name for that group here. And I'm going to emphasize here, what's the charge I need to memorize? But you want to be really careful. It only needs to be charged when it's bonding. When it actually has had a chance to actually combine with things and collide with things, this is the charge that it typically gets. So starting off from lithium, that column there, lithium down to francium, that's group number 1. We call those ones here alkali metals. I'm just going to emphasize for you here, this is lithium all the way down to francium. You notice that it actually ignores hydrogen. Hydrogen, sometimes it's a split personality. It sometimes acts as a metal, sometimes acts as a non-metal, but definitely it's not solid at room temperature, so definitely not referred to an alkali metal. If someone just handed you a block of just pure lithium, so here's lithium, that we would imagine here, that means it's just lithium, 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 lithium. There's no non-metals around. All of those lithiums are no charge. Charges are unstable. What they're going to do is they're going to try to cancel out all charges. Protons match up electrons, so lithium is stable. However, when lithium is actually exposed to oxygen, it can actually react. When it starts bonding, what we're going to find is all these ones here happen to have 1 electron on the outermost shell. Metals also tend to be very large atoms, so they typically get oxidized, and they typically take on a charge of +1. Now, in most cases here, when you're doing naming, sometimes you see +1, sometimes you see it 1+. There is one thing that we're going to see in chapter 3. If you write it as +1, you'll get it right. If you write it as 1+, you actually get it wrong. So most times, I don't really care. To just tell people here is just always do this. Most times it doesn't matter. In the times that it does matter, you already have the right order. Let's put the sign first, and then let's put the number afterwards, or the digit afterwards. Again, in most cases, it doesn't matter. +1, chemists are even lazy. They just might say even just plus. If it's just a plus here, is indicative that's just 1. Let's move on to the next group here. The second group over, we're going from our berylliums downwards from there. So that there, we call these ones here alkaline earth metals. So just slightly different name here. Sometimes you just call them alkaline metals. Both the root word here, alkali, as well as alkaline, both of them refer to being basic. So, for example, like acids and bases, when they neutralize each other, these ones here as metals, they typically form basic solutions. They typically form those hydroxides. More on this a little later. These ones here happen to have 2 valence electrons. So when they start bonding here, again, they would be neutral as a block of metal themselves. But when they start bonding, they typically want to lose those 2 charges. Those ones, memorize them as +2. We alluded to the fact here, group 3 to group 12, so these sort of inner columns here, we call those ones their transition metals. We'll come back in chapter 2 and chapter 3 to actually explain. First thing, these orbitals are actually going to be in what are called d orbitals. The d orbitals are inner orbitals. They are not the same type of orbitals, the same type of shells as the metals nor the nonmetals. So in that case there, in those 2 chapters there will also explain they're different from the regular valence electrons, and they also do a different type of bonding, which actually allows them to have multiple charges. So for the time being, let's just say group 3 through 12, we can call them transition metals. They're sort of in transition. They're sort of losing their metallic character as they approach that stair-step line. In terms of charges, these ones here they have many. So what we're going to say, in the past we used to call these multivalent. Right? Multivalent here meaning, well, many. Valent sort of refers to the valency or the outermost shell. So many, we're just going to use the terminology charges. In chapter 3, when we come back to this here, we're going to write it a different way. We're going to actually call it a variable oxidation state. So variable meaning, well, it can be changeable. Sometimes it's this, sometimes it's this. And oxidation state is a fancy word for charges. So those ones there, so far on our regular grade 11, grade 12 table, on the back of your periodic table, you're actually given for your metals, which typically have more than 1 charge. Manganese can be 2 or 4, chromium can be 2 or 3. There's a handful of them that we have on there. Obviously, your grade 10 table was giving you a whole lot more information. It didn't just pick out the odd elements that they might ask you for. It gave you every single element with their most common charges, actually even listed in the order of which charge is most common. So although they can have multiple charges, which one here is it likely going to be? the most. Even that listing there is not going to be a full, complete listing, but they give you the most common, the ones that you see. It's getting a little bit hard to come up with a group trend as you look at these columns here, because as I step over to what would be group 13 or group 3, in this case here on the top we might have a metalloid, on the bottom are metals. As you go across we start picking up non-metals, metalloids, and metals. It's very unlikely that I'm going to have one charge that belongs to all these here, because there is a sort of division over the stair-step line. So what we're going to do instead is we're going to jump all the way over to the last column, technically group 18, or you can call it group 8. These ones here are all definitely non-metals. There's going to be a common name for those ones. Hopefully you remember that one there. For group number 18, again also sometimes called group 8, these ones are called noble gases. Careful when you spell this noble gases here. Sometimes I do get it spelled incorrectly as a Nobel gases like this. Okay, so it's not a gas that won a Nobel Prize and just one S for there. Okay, noble gases here, in some sense, they were actually called inert gases. That word inert actually means it's unreactive. These are the least reactive families here. These ones pretty much keep to themselves. They just stay as their own atom because they don't really perform any bonding. They, as a non-metal, they themselves were zero because they don't really bond with things here. They're just going to be zero. So they just keep to themselves. We're going to refer to the fact of them having a full shell, somehow making them stable, and basically everything else wants to lose electrons and gain electrons until they look like a noble gas. Let's backtrack one column here over to the fluorine down to the iodine column here. Technically group number 17. This is sort of away from the stair-step line, so these are all non-metals. These ones here are going to be called halogens. Compounds are called halides. And these ones here actually have 7 out of the 8 valence electrons. They happen to be a tinier radius as well. They don't really want to lose electrons. So when these guys actually form charges, these ones here are actually going to be a negative one. So instead of giving you the charges for every single alkali metal, every single halogen, as long as you memorize these group trends here, we're still good. Just before we get into the actual naming of this part here, I want to just emphasize to you as we do these chemical formulas, as we do this writing here, most of the elements, now we know elements here, they're unique types of materials. They all have the different number of protons. Most elements actually occur to us in the monatomic form. Right, so let's break apart that term here. So most of the elements, take your pick here on the periodic table, they occur as mon, which is as a single atom. They just appear as one thing. So back to my example here of lithium. So someone hands you a block of lithium. We would imagine it's lithium, 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 lithium. It's very similar to the lattice structures we're going to see for ionic compounds. The difference here is there's actually no nonmetals. This is just plain old lithium. Even though I just told you earlier, hey, lithium is alkali metal, it should be +1. This lithium here hasn't yet bonded. So this lithium here actually is just lithium. I can just say the lithium atom. If I take a sharp enough knife to it and I can chop it up here, I'll eventually have an atom worth of lithium. It's stable. It has 0 charge. It's perfectly happy having its 1 electron in the outermost shell. And that one single atom of lithium has the same properties as this bulk material has as host sample itself. So most of them occur like this. I can do the same to gold. I can do the same to nonmetals, say selenium. Right. So every element has its own atom, and most of them occur to us as monatomic. There are a few elements, however, that occur as polyatomic. We're going to mainly deal with these here. Some elements, this could become really important as we do our balancing later on. Some elements occur as diatoms or diatomics. So these ones here were seen as, they always occur as 2 atoms. I'm going to make the emphasis here again. When do we need to worry about this diatomic rule is whenever it is elemental, whenever it is by itself. If it's compounded with other things, don't even worry about this, okay? But as long as it's by itself, there are a few elements that aren't stable by themselves. For example, let's take a look at fluorine. Fluorine is group number 17, so it means it has 7 valence electrons. We'll come back in a later chapter and actually draw these diagrams. What we're going to see here is fluorine has a whole host of many electrons. Fluorine actually has an unpaired electron. If fluorine exactly looked like this one here, having that unpaired electron actually makes it a radical. Sometimes they call it a free radical, just to identify this is a super unstable species because it has an unpaired electron. It's going to try to bond, it's going to try to pair up this electron. It doesn't really care if that that pair is actually really attached to something or just paired up and just not bonding to anything. But what it really doesn't like is this unpaired electron. So whenever we have just fluorine in nature, it's never just going to be a simple F atom. It's actually going to have combined it with another F atom here. This F atom here likewise will have that one unpaired electron. It's a radical. They're going to collide together and they're going to actually form a covalent bond and actually stabilize each other. So whenever we see fluorine in any chemical formula, we'll always write it as F2. That's whenever fluorine is by itself. Let's say I bond a fluorine with an alkali metal. I can have LiF. Don't come along and say, oh, fluorine has to be diatomic, F2. Remember, it only needs to be diatomic whenever it is by itself. So there's a handful of elements that look like this one here. Sometimes they even try to scare you away. They might say fluorine gas. By telling you that it's a gas doesn't change the fact that this is just plain old fluorine. I might indicate that it's a gas. I might say bracket G, just like we did on yesterday's lesson. But it just tells you it's just pure fluorine. It's just by itself. So how do we remember which ones there are diatomic? So let me just sketch up for you the rough periodic table. There's 8 of them here. One of them is hydrogen. You can't predict it based on just their unpaired electrons. This is an empirical finding. So hydrogen by itself has to actually occur as H2. On the other side here, it sort of forms like a 7 shape. So it's going to be N, O, and F, Cl, Br, and Iodine. So these ones here, whenever they are by themselves, they always need to occur as 2. So my student teacher used to say it's like having a hockey stick over here and a puck, and those 8 elements there have to occur as 2. So H2 has to be N2, O2, F2, Cl2, Br2, I2. Did I miss one there? Nope. All right. So, so there's 7 diatomics there. So I'll give you a quick memory aid here. You can just however way you memorize these ones, whenever these are by themselves, you have to write that they are 2. First one here, imagine you had a teacher, Mr. or Mrs. Teachers always have very funny names. Let's say you have a teacher called Mr. Hofbrinkel. So that means you have HOF, Br, iodine, nitrogen, and chlorine. Those ones, whenever they're by themselves, it's always going to be paired up. It always comes as 2. The other one is if you can make up an acronym for yourself here. I have no bright or clever friends. Right? I'm sure that's not you. Right? You have many, many bright, clever friends. But in this case here, iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, and fluorine. I did this one year, and my IB class was like, no, we're an IB. I have numerous bright. What have you? Just make sure you memorize. These ones here, whenever they're by themselves, they actually have to occur as 2. There are a couple other odd ones. We're not going to touch on it too much here. Every now and then you're going to see phosphorus actually occur to us as P4. Sulfur actually occurs to us as S8. So just to indicate to you, there are other ones that are polyatomic that are actually different. But usually when we do balancing of those ones, we just usually say P plus something, S plus something. We don't actually have this polyatomic form. That introduces us to just that general name here. I just said most of them are monatomic, some of them are diatomic. You could refer to a molecule as actually a polyatomic. So just a quick aside here. A molecule is actually a polyatomic grouping. Right? If you remember from yesterday, molecule was having more than one. So this one says you have many atoms all grouped together. In a second, we'll switch over. What if this polyatomic here actually has a charge? It's actually a polyatomic ion. In this case here, I just want to just remind you, there's a few common names I want you to memorize. One of them, well, H2O, what is it? Water, right? So you memorize that one there, right? Let's look at NH3. NH3 is actually going to be the common name here, ammonia. Care for the ending. So this is used for a lot of cleaners, things like that. But make sure the ending is ammonia, IA, instead of ammonium, IUM. Ammonia, another one here is methane. So methane, we're going to do a quick section on organic later on in this course here. Methane, meth actually refers to there being one carbon. It's just saturated with the remaining as hydrogen. There's another one here that's very common here. I usually just say chaku. Okay. Chaku here. The full name of this is actually ethanoic acid. We're going to more so refer to it as acetic acid. Acetic acid is sort of like the generic name as compared to the IUPAC name that we have. Now this is a little bit strange here because we look at something, hey, this one here has an OH. Shouldn't this be a base? Shouldn't it be an ethanoic base? Something like that. In this case here, this is getting us into a little bit organic. Just I want to indicate to you what's happening here. If I draw this structure, we'll draw these pictures here in section number 4, you're totally right. This OH group here would be what otherwise would need to be a base. However, to be a base, you actually need to be able to release this OH in solution. Turns out in this case here, the carbon and oxygen bond here is fairly strong. When you drop this in water, it's not this bond that breaks, it's actually this bond that breaks here. Because we're actually able to release an H plus instead, when this gives off that proton, it makes us here an acid. For the time being, just memorize these ones here are going to be acids. So, with that background in mind here, let's just switch over to ionic naming, or ionic nomenclature. We can sound really fancy here. Ionic nomenclature. So there's two types of compounds in our world. Ionic is one extreme, covalent is the other extreme. For the purpose of this lesson here, I just want to indicate to you, how do we tell whether it's ionic or covalent? Slight simplification here. For an ionic compound, we imagine a compound made out of metal and a non-metal. For us, when we're doing our rules here, the metal always comes first. Some other things that we know about ionic compounds here is we actually have transfer of electrons. So let's just say electron transfer. And in fact, what's happening here is the metal oxidizes. That word oxidize means lose electrons. Metal oxidizes, losing electrons. So the non-metal reduces, gaining them. So that's what we refer to as an electron transfer. The metal is completely losing the electron, tossing away its electron. Now, usually when you think about, when you lose things, you're going down. In this case here, the things that I'm losing themselves have negative charge. If I had no charge to begin with, and I throw away things that are negative, the metals will gradually end up forming cations. They end up forming positive ions. The nonmetals, they are reduced. Again, usually when you say reduce, the number is actually going down. They're actually reduced by gaining these electrons. When they actually grab extra electrons, the nonmetals themselves, they actually become negatives. So these ones here actually form anions. You can check that against the common trends we said earlier. Great, alkali metals were +1, alkalines were +2, whereas your halogens were -1. That's all consistent. Let's just go through a few different families of ionic nomenclature, and then we'll get through a couple new families in the next lesson. First category here, we're going to refer to these as binary ionic compounds. And I'm going to give you just a generic formula here. Like I mentioned, it needs to be metal first, and then the non-metal afterwards. Simple as that. We're going to be changing the ending of the non-metal, and we're going to change the ending to an IDE. So for example, let's take the symbol here, NaCl. You look on your periodic table here and you can say, great, I know it's ionic because Na is metal. The metal came first. Let's name the Na. Na is sodium. The Cl here should be chlorine. And then we just change it because it is in the compound form. We change the ending to chloride so it's a little bit easier to say. Don't come back to me and say, wait, I thought chlorine was one of your Hofbrinkel ones. Chlorine here has to be 2. Remember, it only had to be 2 whenever it was by itself. When it was just chlorine gas, this is not chlorine by itself. This is chlorine actually bonded to sodium. Let's do another compound here. Let's do magnesium with the F there. So I want to practice the naming with you here. Strangely enough, again, the symbols are giving you a little more information. They're actually giving you, for Mg, there's actually a 2 here. Now that 2 here is coincidental. It's not because of diatomic. But let's just go with the word name. Look in your periodic table. The Mg here is an alkaline earth metal, magnesium. If you look at its charge, alkaline earth metals, when they're bonding, they should have +2. Fluorine is a halogen. Fluorine should have a charge of -1. Magnesium fluoride is just a word name. You notice that there's no indication that there has to be a 2. We're going to add a rule here. Because charges are unstable in our world, the rule is the sum of the charges equals 0. They're going to play around with electrons, passing electrons, gaining and losing electrons until their charges actually cancel out. So for example, if I have just one Mg bonded with one F minus, the +2 -1, I still have a net of +1. Now fluorine doesn't want to have -2, don't come along and change the charge, but what if magnesium was actually bonded to more than one fluorine, both of which are -1? In that case there I have +2. Great, it cancels out the -2 here. Sum of charges cancel it out, and therefore we have the compound MgF2, albeit these ones here are actually ionic bonds as opposed to what looks like a covalent bond right now. So we do need to look out for those charges here. Let's try to go the other way. We need to go, let's go aluminum. Sometimes they write down aluminium. It's exactly the same element here. Aluminum oxide. If I want to write out the formula for it here, I need to work out the charges. I need to work out so that the plus and minus cancel out. Aluminum, you're going to find it on the back of your periodic table. Aluminum is going to be +3. Really, if you had to guess on the periodic table, looking at the group trend, we had group 1 as +1. Group 2 as +2. So +1, +2. We're going to skip over these ones here because they're transition metals. If you had to guess, I would have guessed these are +3. That's where aluminum is. These are +4. These are +5. We basically sort of match up column by column. For your non-metals, your noble gases start off at 0. If you had to guess, halogens are -1. Had to guess oxygen. In this case here, we're going to guess oxygen, group number 16, so -2. Those are just some general trends here for metals and non-metals. They sort of mark off how far away I am from the noble gas. So what ratio would I need between aluminum and oxygen for these charges to cancel out? Let's start off, well, right now I'm overly positive. I have 3 -2, I have a net of +1. Let's add another negative. Oh no, now I'm a -1. Now I'm going to tack on another +1 here. Now I'm overly positive again. Eventually we're going to hit the lowest common multiple. Well, both 2 and 3 go into 6. And therefore my ratio should actually be Al2 and oxygen 3. These ones here are called subscripts, and they just identify for me in the compound. I would expect this proportion for every 2 aluminums, there should be 3 oxygens with it. That's your typical ionic compound here. It's a binary compound. Let's throw in 2 little twists here. Second category here, we can do our multivalent metals. We saw that term earlier here. Again, the generic format is going to be metal, but this time we're actually going to add a Roman numeral. Because these ones here are actually multivalent, the Roman numeral actually shows the charge. If I have an element that can have multiple charges, I want to know in that particular compound what charge is actually using, metal with the Roman numeral and the non-metal. I only do this for things that have multiple charges. Like I said, chemists are lazy. I don't want to go back and I don't want to say something like, oh, aluminum is 3+, aluminum 3 oxide. I know aluminum is 3. It's always going to be 3. It's only when they have multiple charges. You check the back of your periodic table. They give you the couple odd positive cations here, and you go from there. So either from your grade 10 data booklet here, it says iron can be the +3 or the +2 form, or on the back of our periodic table, we're going to find that as well. Let's bond iron when it uses its +3 or it uses +2. Let's bond it with that same oxygen. When I have compounds of iron oxide, that actually forms rust. In this case here, when charges have to cancel, because the iron might be 3, might be 2, the ratio that ends up forming is actually a little bit different. In this case here, 2 and 2 perfectly cancel out. My compound can just be FeO. I could have called this just iron oxide. But what charge is iron using here? In this case here, iron is currently using its 2+. I'm going to do the Roman numeral 2 there. When iron is using its 3, the word name here would actually be iron 3 oxide. This one here is almost identical to the aluminum one that we had from earlier. Iron, like aluminum, had a +3, so the ratio ended up being Fe2O3. So you see those proportions are different here, although there's going to be similarities because they're still made out of iron and oxide. That proportion there actually gives it slightly different behaviors, maybe a different melting point, maybe a different reactivity. So careful of those multivalent metals. Only use Roman numerals. I'll count 8 for you here. 1, 2, 3. 4 is an IV. V is 5. VI 6, 7, 8. If you really wanted to go up to 9 is IX and whatnot, but usually by the time you get a charge of +7, +8, you pretty much lost all your electrons in that row. I don't really want to lose any more beyond that. Last but not least here, I'm going to throw in those polyatomics here. Earlier I mentioned here the polyatomics are just another name for molecule, but specifically here now we're going to say these are polyatomic ions. Sometimes we shorthand this PAI, so just be careful of that. So polyatomic ion is a many-atom grouping. So far that's just a molecule, but because it has the word ion, we know this is actually charged. So these ones here, let's say I have the compound Na2CO3. I'm tempted to come along and say sodium carbon oxide. it's never so complicated like that. Most of our polyatomics here are anions, so I would expect a lot of groupings here on this side. I'm just going to name the metal, name the non-metal. In this case here, the only rule here is check the table. So check the back of your periodic table for the common name. And just use the common name for that grouping. Don't try to name it yourself. So in this case here, I recognize Na as a metal, so I can say sodium. Instead of trying to come along and say, oh, carbon oxide, something like that, that grouping is actually referred to as a grouping carbonate. Most of your polyatomics will end in ATE and ITE. We'll make use of that in tomorrow's lesson. Because it already has an ending, we don't change it to IDE. Now, the one thing you need to be careful of here, let's say I practice the other way. What if I wanted the compound here, ammonium sulfate? Sulfate sometimes is spelled with a F or a PH, doesn't really matter. You look on that back side of the periodic table again, ammonium, different from the ammonia from earlier. Ammonia was NH3. This is the polyatomic grouping NH4+. Sulfate is the grouping here SO4 with a -2 or 2- is fine. In this case here, both of these are polyatomic grouping. This is really the only polyatomic that has a positive charge, so I definitely memorize this one. If I see NH4, I know the common name is ammonium. I already have the common name, ammonium sulfate. I still need to work out the charges though. How many ammoniums would I need to counterbalance the sulfate having a -2? Because I have a +1, I need 2 ammoniums to actually counterbalance. So therefore my formula is going to be NH4. Well, I need 2 of them and a sulfate. This part here gets to be a little misleading. To show you that it's 2 of the entire grouping, I'm going to put a bracket around that NH4 there. So there we get the compound, ammonium sulfate, common name for ammonium, common name for sulfate. Don't change the ending. If it ends in ATE or ITE, it's probably a polyatomic. You just check that common name. So we'll pick it up from there tomorrow. Make sure you practice your worksheet with naming ionic compounds. Thanks, guys. Take care.